So this is number 32. Number 32. Yes. Yeah, because I scanned that package in to make sure that it did. Okay, quiet please. Quiet please. So this question, Haley, this question, you know, it's actually about domain and range too. But it's not a set of points. You know, different than the homework problem where we had, 4 x values and we got 4 y values, or 4 and 4. This thing we would have to graph. If you have to look at find the domain and range of an equation, then we need to graph it. So let's do that. You should use your calculator. Try it. Trying to help you here. F of x. So I'm going to put in 2x minus 1 in parentheses, right? 2x minus 1, parentheses squared, plus 4. Okay, and then I'm going to zoom, normal zoom of, okay, let's second, y equals 1 off, then graph. So, yeah, I mean, we did a very little bit with the shape, but that's a parabola, right? Because that's a squared, x squared, basically. It's going to have a shape that's kind of like a U, right? Now, how many points make up that U? Infinitely many points, right? It's not just a finite set of points. So if we were trying to do domain and range here, we couldn't just, like we did in the homework problem, use set brackets and just write out this list of points, because we'd be going on forever. There's infinitely many points on here. So when you do the domain and range of a whole graph, you're going to have to use inequality symbols. So in this case, we're just going to take it at their word. They said the domain is all real numbers, which it is. Meaning you can plug in anything in there. There's no issues for any value of x. But the range, it looks like the parabola comes down and then it goes back up again. So it doesn't look like the y values are all real numbers. They don't go infinitely down. So how far down do they go according to this graph? Positive 4, so the answer is 4. So they said in their answer, the range is all real numbers greater than or equal to, and it looks like it's 4, right? Because the range are the y values. You know, and usually the way that would be written is something like this. You would just say y. I got to change my pen. Y is greater than or equal to 4. That's the range. To me, that's on the edge of what they ought to be really asking us here in this class. But okay, now, which function has exactly 1 0? This is number 33. So what are you going to say, Hunter? And what would you be looking for on it again? What are you looking? What are the zeros when you graph it? What are the x-intercepts, right? So yeah, exactly. So you could graph all 4 of them and see which one crosses the x-axis or touches the x-axis exactly 1 time, right? I mean, if I go through this process like on the first one, right? Go to y equals, and I'm going to go 2 times parentheses x plus 3 times x minus 3. And then I look at the graph. How many zeros do you see? 2. 2 x-intercepts, 2 zeros. So it's not going to be that one. Now, you could have told that without graphing. I mean, since it's already in factored form, I could have told you the zeros are -3 and +3. So in fact, like, you don't really have to graph. If you could, for example, could you tell me What are the factors of 4 that add up to 5? 4 and 1, that's two different, going to end up with two different zeros there. But you could graph it to make sure about that. How about x squared minus 16? How does that factor? That's difference of squares. X plus 4, x minus 4. How many zeros? 2. Try to put that one in the calculator. Right? Try the letter D. Right? Clear. X squared plus 8 parentheses x plus 2. And then you graph. And how many zeros do you see there? How many x-intercepts do you see? 1. Yeah, it looks like it's just 1. Can you see what the value is? Well, to be sure, go to the table of values. Second, table of values, scroll up and see whether it just happens to show up. Yeah, look at that. When x is -4, y is 0. So that's the 0. Second, graph. And that's how you get the table of values. Again, what are you looking for to find the x-intercept? Looking for those points where y equals 0. So the answer is D. In the end, the answer is D. So you could do this. You could have done this problem without graphing, but graphing will definitely work. You know, don't make it harder on yourself. Okay, which one of those has a y-intercept of -6? How do you find a y-intercept of a function? You substitute x equals 0, because in the y-intercept, the x is 0. So, I mean, you could do that. You could like put in a 0 for x and then calculate. Or put it in the calculator, right? So let's say I do the first one, letter A. Clear. -2 parentheses x minus 3 squared plus 2. Right? And now if I look at the graph, you know, -16 is going to be like probably off the screen on the bottom. But if I look at the table of values, right, the y-intercept should be where x equals 0. So for letter A, what is the y-intercept? X equals 0, y equals -16. So that's it. It was letter A. Right? So when you want to find the y-intercept, look for where x equals 0. If you want to find the x-intercept, look for where y equals 0.
So, Mr. Callahan.
Yes.
So you said you fill that, you put in the calculator exactly like this, right?
Yes.
Hold on, let me do that. And then when you hit graph, you get this. And then how do you find out the equals?
Do the second graph for the table of values. Look for x equals 0.
Oh, okay.
What does y equal? There you go. That's the y-intercept. What's that? That's the y-intercept. For the y-intercept, look for where x equals 0. For the where's an x-intercept? It's actually on my screen anyways. Look at there, y equals 0, so that's an x-intercept too. I mean, I kind of made a note to myself when I looked at the test that x and y intercepts come up. They come up a little bit. So you might, be familiar with those two things, right? The y-intercept is where x equals 0. The x-intercept is where y equals 0. Okay, so the answer to that one was A. Next. Okay, here's a function, and they actually didn't say f of x, they said h of x, but that's allowed. That shouldn't confuse us too much. How would you find h of -2 if you have a formula for h of x? You plug it in, right? So I could go like this. I could say 12 times -2 to the third minus 15. Okay. So now you got a couple other options here. I mean, number one, you could go like, just since we've been doing this, why don't you put that function at y equals, and then just go to the table of values where x equals -2, the answer is in the y column, right? If I go to the y equals, clear, I'm going to put 12x to the third hat 3, right arrow to get out of the exponent, -15. And then I don't need to look at the graph. I'm going to go to the table right away. And let's see, where x equals -2, what does y equal? -111. Yep, that's the answer. That is h of -2, with whatever the y value is right there. Another thing, what's that? Let's see. Because you didn't put in that x. You have no x in there. Oh, you just put it in like there. Yeah, that's okay. That'll work. Sorry. But another thing you could do, because if these are confusing to plug into, you could always like store a value, like store x equals -2, and then do 12x to the third minus 15, and it'll do it the whole thing. Yeah. Does it make a difference if you do it that way? If you're gonna do the store a value, you should use the letter and not the number. Store the number for the letter and then type it in. That way, if there's any kind of confusion, like does the negative get squared or cubed or things like that, it'll get it right. Sometimes we make wrong decisions on those, but that's why the store a value thing works. It helps to eliminate some mistakes when it comes to order of operations, things like that. Okay, so this one was, what did we say, -111? Yeah. -111? Again, that's the non-multiple choice kind of problem that we really want to get those right. I really believe we'll get a lot of the multiple choice right, but we can try to do better on those. Okay, now we need to do a little bit of review. This is stuff, we did this stuff before, right, which is direct variation. A direct variation is a straight line that goes through the origin. These are just like notes so that we can address some of the problems in the package next. Okay, so an example of a direct variation is something like y equals 2x, right? I mean, that kind of looks like y equals mx plus b, but it's missing something. Right, it's missing the b. So what does that tell us about the value of b? It's 0, right? So in fact, the b equals 0, and that's why it goes, a direct variation always goes through the origin, right? So in tests like these, there's always going to be one question where that one fact is going to solve it for you. If you just know that one thing, it's probably going to get you a value. Now, 2 is the 2, that number that's in front of x is called the constant of variation, or sometimes it's called like a constant of proportionality. The SOLs call it that more. But if y equals 2x, then it must be, if I just divide by x there, that y over x equals 2. So now, how many points make up this line? Infinitely many points, right? Every point has a different x value and a different y value. So x and y are not constants. But if you divide y by x in a direct variation, that has to be a constant. That never changes. So, I think we're good to go. What happened there? So next. Okay, so also, if you got an equation like y equals 2x, right? If I increase the value of x, what is that going to do to the value of y? They have to increase, right? If x is 2, then y is 4. If x is 4, then y is 8, right? If x decreases, if x is 1, y is 2, right? So they change in the same direction, right? An increase in one variable means an increase in the other. A decrease in one variable means a decrease in the other. Okay, so now let's look at a couple problems from our package. This is the number 37. It says, look at these different situations in the table. Which one of these describes a direct variation? And now if we read the first one, I'll give you a flavor of what they're doing here. As the number of heartbeats per minute of an animal increases, the life expectancy of the animal decreases. Does that sound like a direct variation?
No.
Because one's increasing, the other's decreasing. That's not what direct variations do. So not number one. How about number two? The power of a gear mechanism increases as the radius of the gear increases.
Mm-hmm.
Yeah, they both are changing in the same direction. That's it right there. And just to be sure, you know, if we didn't misunderstand something here, we can check the last couple, right? So this one has decreases and increases, increases and decreases. So, you know, all three of those, 1, 3, and 4, not good. But the number 2, 2 increases, that's it. So that would be letter B. Right, and that's because of that and that. Okay, which one of those graphs shows a direct variation? Remember what you expect to see. You're looking for the y-intercept equals here. It goes to the origin, right? The middle of the graph. So the only one that does that is B. Again, if you know that one fact, you're probably going to get at least one of these questions right. Right, and that's because of that right there. Okay, inverse variation. An inverse variation would be like y equals 2 divided by x. Right, the x now is in the denominator. Now what happens to the value of a fraction if you increase the value of the denominator? It goes down, like it's 2 over 4 is 1/2. 2 over 2 over 8 is 1/4, right? So it's going to go down. So as x increases, y decreases. What's going to happen to the value of the function and y, or the fraction and y, if x decreases? It increases. As the denominator decreases, the fraction increases. So they vary in opposite directions. That's called inverse variation. I mean, when things vary inversely, that's not just like a math concept. That's the kind of thing like you could read that in a newspaper article. They could be talking about, you know, 2 different kinds of numbers and saying, and they are inversely related or something. And they're not asking you to come up with formulas or anything. That's kind of a common understanding. That means things are varying in different directions. One goes up, the other goes down. Okay, and now, if y equals 2 divided by x, if I multiply by x, then I get xy equals 2. So now we're not dealing with the graph of an inverse variation. That's a more complicated graph than we have to deal with in this class, but it's made up of infinitely many points, right? And everyone has got a different x value and a different y value. So we're not saying that x is a constant or y is a constant, but if you multiply x times y in an inverse variation, that is a constant. That never changes. And it's not always 2. I'm just using 2 as an example, okay? Could be xy equals 4 or 10 or negative 5. Yeah. Sure. Okay. So that's inverse variation. So this is number 41 in your package. It says which one of those tables shows that x and y vary inversely. So let's see. If I look at letter A, right? As the x values are increasing, the y values are increasing. Does that sound like an inverse? No. Okay, how about this one? as the x values are increasing, the y values are increasing? No. Okay, the x values are increasing, the y values are decreasing. Could be, okay, but what's the check? Multiply x times y. What is 1 times 10? 2 times 5. 5 times 2. 10 times 1. Okay, there you go. It's inverse variation. 10. So the check is multiply. Multiply the x times the y. I'll write it over here in the column. X, y. 10, 10, 10, and 10. So because those are all the same, since x, y equals 10, that is the inverse variation. And the equation for it, y equals 10 over x. Now, I mean, they didn't actually trick us here at all because, you know, these were increasing too. I mean, they could have had like two of these tables of values where one increased and the other decreased, but it didn't pass that x times y test. But that was actually this one you wouldn't even have to do the check. Just look for increasing and decreasing. And last slide. Okay, 38. So a student traveled to a foreign country on an airplane. It took 18 hours to arrive at its destination, and the plane was traveling 900 kilometers per hour. When returning home, the same trip only took 15 hours, going at a speed of 10,080 kilometers per hour. If t represents time and s represents the speed of the plane, which statement is true? Right? Letter A, the time it takes for a plane to travel a distance varies directly as the speed of the plane. So they're trying to get us to say, does this sound like a direct variation or inverse variation? And let's see. So the numbers that we've got are going in one direction, we had an 18 and we had a 900. Going in the other direction, we had a 15 and a 1080. Right? So if this is a direct variation, it should be that when you divide, right, y over x, that you get a constant. So what is 900 over 18? 50? Okay, what is 1080 over 15? 72, right? So those are not the same. Therefore, this is not a direct variation. Okay, that was a check for direct. Okay, thank you. Okay, now we're going to check for inverse. If this is inverse, then it should be x times y is constant. Okay, so what is 18 times 900? 16,200? Okay. What is 15 times 1080? 16,200. So in fact, it looks like x times y is constant. That means it's an inverse. So let's see. Letter A says varies directly because TS is constant. Well, that's wrong because it doesn't vary directly. It varies inversely because S equals 50 times T. No, because S equals 50 times T, that's a direct variation. So that's wrong. Okay, it varies directly. Well, no, it doesn't. It varies inversely because T times S, that was the time times the speed, equals the constant. That's the right answer. So you got to remember the two checks, right? For direct variation, check y divided by x. For inverse, check x times y. And the answer is D. Okay. And that's it. That is homework. And it's actually related to direct and inverse variations.